I have a question for you. Take a look at this equation. X over 2 to the sixth equals 3 to the sixth. At first glance, this doesn't seem too difficult. In fact, you might already have an answer in your head. And honestly, I did too. But then I noticed something that completely changed how I looked at this question. Read the instruction carefully. Find all 6 possible solutions. 6? That one word completely changes everything. So before we start solving, see if you can spot where those 6 answers might come from. Let's investigate. If you're anything like me, your first instinct is probably take the 6th root. And to be fair, that's not a bad instinct. In fact, Literal will discover that it gives 2 perfectly correct answers. But only 2. The problem is, this question promises 6. So before we rush into taking roots, let's see if there's another path. Sometimes, rewriting an equation tells us much more than solving it immediately. Let's begin by simplifying the left-hand side. Before we do anything else, remember this law of indices. When an exponent is applied to a fraction, it applies to both the numerator and the denominator. So, instead of treating the bracket as one object, we raise both parts to the 6th power. The x becomes x to the 6th. The 2 becomes 2 to the 6th. Nothing mysterious happened. We're simply using a rule we've known all along. Now our equation contains a denominator. If we want x to stand on its own, that denominator has to go. So what should we multiply both sides by? Exactly, 2 to the 6th. On the left, the 2 to the 6th cancels with the denominator. That's exactly why we chose it. Now look at the right-hand side. We have 2 numbers, both raised to exactly the same power. That reminds us of another law of indices. If the exponents are the same, we can multiply the bases first and keep the exponent. Watch what happens. 2 times 3 becomes 6. The exponent doesn't change. And just like that, our equation becomes x to the 6th equals 6 to the 6th. Now that's a much cleaner equation than the one we started with. But don't let its simplicity fool you. The real puzzle is only just beginning. We've simplified the equation beautifully, but here's a question. Can we factor an equation when the expressions are on opposite sides? Not really. Factoring works best when one side is 0. So let's move everything to the left-hand side. Subtract 6 to the 6th from both sides. Now the right-hand side becomes 0, and that gives us something much more useful. X to the 6th minus 6 to the 6th equals 0. Now we're finally in a position to start factoring. Now let's look closely at these 6th powers. At first, they don't look familiar, but maybe we can rewrite them. Remember, 6 is the same as 3 times 2. So, raising something to the 6th power is the same as cubing it and then squaring the result. Watch. X to the 6th becomes x cubed all squared. And 6 to the 6th becomes 6 cubed all squared. Now something interesting appears. This no longer looks like a 6th power equation. It looks like 1 square minus another square. There it is, the pattern we've been looking for, difference of squares. Whenever we have 1 square minus another square, we can split it into 2 factors. Let's match the pieces. Our first square is x cubed all squared. Our second square is 6 cubed all squared. Applying the identity gives us x cubed minus 6 cubed multiplied by x cubed plus 6 cubed. One complicated equation has suddenly become 2 much smaller ones. Now another important question. How do we solve an equation when 2 expressions are multiplied together? We use something called the zero product rule. It says if 2 numbers multiply to give 0, then at least one of them must be 0. So instead of solving one equation, we now solve 2. The first is x cubed minus 6 cubed equals 0. The second, x cubed plus 6 cubed equals 0. Each of these equations is about to reveal more hidden structure. Let's begin with the first cubic equation. X cubed minus 6 cubed equals 0. Now here's another identity worth remembering. Whenever we have one cube minus another cube, we can factor it into two parts, a simple linear factor and a quadratic factor. Let's match the pieces. Our A is x, our B is 6. Substituting them into the identity gives us x minus 6 multiplied by x squared plus 6x plus 36. One cubic equation has now become two much simpler factors. Now let's work on the second equation. This one looks almost identical. There's only one difference. Instead of a minus sign, we have a plus sign. That means we switch to a different identity, the sum of cubes. Notice how similar the formulas are, only the signs change. Substituting x and 6 gives us x plus 6 times x squared minus 6x plus 36. Now our original equation has completely unfolded into four separate factors. Let's put everything together. We now have four factors multiplied together, and since their product is 0, at least one of these factors must equal 0. Instead of one large equation, we've transformed it into four smaller equations. Two of them are linear, two of them are quadratic. Let's solve them, one at a time. Let's start with the easiest equations. The first one says x minus 6 equals 0. Simply add 6 to both sides, so our first solution is positive 6. Now the second, x plus 6 equals 0. Subtract 6 from both sides, and we get negative 6. Exactly the two answers we expected from the very beginning. But remember, the question promised 6 solutions. We've only found 2. That means the remaining 4 must come from the quadratic equations. Now for the first quadratic. Whenever a quadratic won't factor nicely, the quadratic formula is our best friend. Let's identify the coefficients. A equals 1, B equals 6, C equals 36. Substitute them carefully into the formula. Everything looks perfectly normal until we reach the discriminant. 36 minus 144. That's negative 108. A negative number under a square root tells us something important. We've stepped beyond the real numbers and into the complex numbers. Evaluating the square root gives us two new solutions. Negative 3 plus 3 root 3i and negative 3 minus 3 root 3i. The second quadratic follows exactly the same process. This time, the only difference is that b is negative 6. Everything else stays the same. Using the quadratic formula gives us two more solutions. Positive 3 plus 3 root 3i and positive 3 minus 3 root 3i. Let's take a moment to look at everything we've found. 2 real solutions, 4 complex solutions, 6 solutions altogether. Remember how this journey began? We thought the equation had only 2 answers. We weren't wrong. We were simply looking at only the real numbers. By patiently rewriting, factoring, and solving every factor, we uncovered the complete picture. And that's one of the most satisfying things about mathematics. Sometimes the answer isn't hiding, it's waiting for you to keep going.